Did you ever wonder where the periodic table came from?
All the time.
It didn't find it under a rock or something. It has its roots back in 1869. A Russian chemistry professor named Dmitry Mendeleev noticed that certain groups of elements had similar properties. And back then, there were a lot of elements that had not been discovered yet. And there was no real great way to organize them, like into this table. So he was looking at them and he found that if he took those elements and put them in order of increasing mass, he would see those similar properties recurring in a repeating or periodic pattern. So it's a little bit like the notes on a piano keyboard, right? So here's 1, and then 8 over is this one, and 8 more is that one. So helium and neon and argon all have similar properties. And he summarized those observations into what's known as the periodic law. When elements are arranged in order of increasing mass, certain sets of properties recur periodically. And that's where periodic table got its name. And there we go. So he organized the elements that were known at that time into a table with rows and columns, arranged so that elements that had similar properties were in the same column. And so it might have looked something like this. This is just the first 20 elements. You'll notice that hydrogen is orange, but it's over here. We'll find out that hydrogen is an exception to like almost every rule there is. He's like the baby brother of the family. None of the rest rules apply to him like everyone else, right? So in Mendeleev's table, there were some gaps, and he predicted that elements would be discovered to fill those gaps, and he even predicted some of the properties of those elements very accurately, as it turns out. This kind of shows you when things were discovered. So things in the light blue, medium blue, and some of the purple ones were known to exist at the time of Mendeleev. And some of the others are much more recent. Hey, I got a chuckle. I didn't read it this time. Maybe that's the secret. Tetris, anyone?
Yeah.
Okay. So in our modern table, the elements are arranged by atomic number instead of mass. It's almost the same, but not quite. And of course, our modern table contains more elements than Mendeleev's original table. So we can look at different sections of the periodic table. This particular table is illustrating where the metals are. It's all those, I guess that's yellow. No, it looks more yellow up there. All the yellow elements are considered metals. The green ones are nonmetals, and the purple ones are metalloids or semimetals. So metals, not metals, kind of sort of metals, right? You should be able to identify whether an element is a metal or a non-metal just from its position on the periodic table. So there is a stair-step line, this darker line coming through here. That separates the metals from the nonmetals, and the semimetals are going to be found on each side of that. The only exception that you need to remember is aluminum. Hopefully we all recognize that aluminum is a metal, right? Your cookie sheets at home, all kinds of stuff made out of aluminum. Polonium is also a metal, but we don't care about him. If you have trouble remembering which side is which, pick an element you know something about. Iron. Is iron a metal? Yeah, it is. So all these guys are metals, and those are the non-metals.
Boron's
Boron is a semi-metal, yeah. Yep. So these different categories have some properties in common. Metals are good conductors, both of electricity and heat. They're malleable and ductile, meaning you can hammer them into a sheet or draw them into a wire. They don't shatter when you hit them. They're often shiny, and what's most important in chemistry is they tend to lose electrons in chemical changes. If we look at the properties of the nonmetals, they're almost like the antimetals, right? Metals are good conductors, nonmetals are not good conductors. They're not ductile, not malleable, and instead of losing electrons, they gain electrons in chemical changes. The metalloids, sometimes called semimetals, have mixed properties. They're just literally between metals and nonmetals. Some of them are considered semiconductors because they have an intermediate electrical conductivity. Nonmetals are non-conductors, metals are conductors, semiconductors are in the middle. They conduct some, and that conduction is temperature dependent, and so that makes them extremely useful for things like computer chips. Another way we can look at the periodic table is by looking at the periods and the groups. So when we talk about periods, we mean rows. So these are the rows, and we talk about groups, we're talking about columns. Not exactly sure why they didn't use row and column, but whatever. So here again, this one's color-coded. We have these yellow elements over here and the yellow elements over there. Those are considered the main group elements. And the blue ones are considered the transition elements. They are a transition from this side to that side. This reminds me of a river. Here is a sandy bank, and there's the river, and here's the other bank. This is the color blue and yellow for sand, I don't know. The periods are numbered 1 through 7, and those numbers will appear on a periodic table, just like they do on this one. The groups are also numbered. There are 2 different ways of numbering the groups. The official way is just 1 through 18, but in the US we typically use these other numbers, 1A, 2A, etc. The transition metals have group numbers. We're not going to care about them at all. But the main group element group numbers are going to be important. And so this is 1A, 2A. Over here, we see there is something similar between the 2 different ways of numbering. This is 3A, that's 13. So if you get rid of the 1, then they're the same. 3, 4, 5, 6, 7, 8. So elements in the same group, in the same column, have similar properties, and some of these groups have special names. The noble gases are in group 8A. Let's see, do I have a picture of that? No, I don't. No, that's these guys over here. Those are the noble gases. They are very unreactive. The alkali metals, those are group 1A metals. That's not what I meant to do. These guys over here, is hydrogen a metal? No, it's a gas, right? What's he doing hanging out over there? Well, there are some properties it has that are in common with the alkali metals. You could also argue that hydrogen should be over there. Again, he just, does whatever he wants. But these are the alkali metals. They tend to be extremely reactive. Throw a chunk of sodium in your swimming pool and big boom splash, right? Not a good idea. These are the alkaline earth metals in group 2A. They're very reactive, but not as reactive as group 1A. And then over here, group 7A, these are called the halogens, fluorine, chlorine, bromine, iodine. And they're also fairly reactive. Those are fairly reactive nonmetals. So we mentioned that atoms can gain or lose electrons to form ions. And so what we'll see is the main group metal will lose electrons, forming a cation. Remember, cations are positive. And it will do this so that it has the same number of electrons as the nearest noble gas. So let's look at sodium. We'll look at the periodic table on the wall because I don't want to lose my highlighting. So sodium is element number 11. How many protons does it have? 11. Not a trick question. How many electrons does it have? The same as the protons, so also 11. Okay, and then let's compare that to neon, element 10. They seem to be on opposite sides of the periodic table, right? But really, you could just bend this around and it could just be a big spiral. So neon has 10 protons and 10 electrons. When sodium loses one electron, now it has 10 electrons. And we'll see throughout the class that a lot of these changes occur so that elements can be more like the noble gases. As a result of that, main group elements are going to form cations with the charge equal to the group number. So group 1A, positive 1. Group 2A, positive 2. Group 3A, positive 3. So for the nonmetals, main group nonmetals gain electrons. They're going to form anions. They're also going to do that to have the same number of electrons as the nearest noble gas. So if we look on the other side of neon at fluorine, fluorine is number 9, 9 protons, 9 electrons. Fluorine tends to gain 1 electron, giving it 10 electrons, which is the same number as neon. So I mentioned that you can think of the electrons being on the outside of the atom as like your outward appearance, right? Your hair color, the clothing that you're wearing, you can change that, but you can't change what's on the inside, who you are, right? So the nucleus is who the element is. That cannot change, except for in nuclear reactions. But the outside can change. And so I kind of think about those noble gases as being like the in crowd, or those cool kids in high school that everybody wanted to dress like because somehow they thought that would make them popular. I don't know. But we'll find out that all of these metals and nonmetals that are like 1 or 2 rows over from the noble gases, they're going to gain or lose electrons to have the same number of electrons as the noble gas. When that happens, they do not become a noble gas. They just masquerade as a noble gas. So the main group elements are going to form, the nonmetals, are going to have a charge equal to the group number -8, and I'll show you a simpler way to remember that in a minute. And then in between those transition elements, very squirrely. You can't really predict what charges they're going to have. Most of them will do more than 1 charge. So alkali metals, group 1A, are going to form +1 ions. Alkaline earths in group 2A, +2 ions. The halogens, like fluorine I mentioned, group 7, those will tend to form -1 ions. And so if we take the group number and subtract 8, we get the charge. The oxygen family, which I think deserves its own special name, but doesn't. Group 6A, 6 minus 8, those are going to make -2. So some people like that. This is, I think, a more fun way to think about it. So if we're trying to predict the charges of these nonmetals, we're going to pretend we're playing a board game, and the noble gases, this is the starting row. So if I want to know about phosphorus, I'm going to start over here, and then I'm moving my piece backwards, right? So -1, -2, -3. Phosphorus is going to have a -3 charge. If I'm interested in selenium, this is 0, -1, -2. Same as group number -8, but doesn't seem to involve math. And then these guys, group 1A, +1, group 2A, +2, aluminum in group 3A, +3. Okay, any questions? Predict the charges of the monatomic ions formed by these main group elements. Monatomic means monoatomic, one atom. So it's not like nitrate or anything funny like that. So nitrogen. The first step is to locate it on the periodic table. Can you find it? Yeah, it's right here. So what charge would it have? -3. 0, -1, -2, -3. And if we're going to write that, write a symbol for that ion, it's the element symbol and then the charge as a superscript. Number first, sign second. If it helps you to remember, I think of this as being intentionally different from exponents. We don't want us to look like the variable n raised to the -3 power. Okay, rubidium. +1. So we find rubidium down here. We don't need to know his name to find out his charge. But there it is. And this is in group 1, so it has a +1 charge. And so we would write the symbol Rb plus. Chemists tend to not write ones unless they absolutely have to. If you wrote Rb1 plus, we would know what you meant, but we might snicker behind your back. Any questions?